Right now, light is racing across the universe at 670 million miles per hour, the fastest that anything can possibly move. At that speed, a single beam of light could circle the entire planet Earth 7.5 times in the time it takes you to say the word now. Light from our sun crosses 93 million miles of empty space to reach your eyes in about 8 minutes. Light from the nearest star beyond our own travels for more than 4 years before it arrives. Nothing in all of physics moves faster. Light is the universal speed limit, the one unbreakable rule written into the structure of reality. And yet there are places scattered throughout this universe where even light, the fastest thing that exists, is not fast enough to escape. We call these places black holes. They are regions where matter has been crushed so completely, where gravity has become so overwhelming, that the speed required to climb away exceeds the speed of light itself. Anything that falls in, any particle, any spacecraft, any beam of light, any person, can never come back out. Not because the engines are too weak, not because the distance is too great, but because there is no longer any direction that leads away. Here is what will shatter everything you think you know about gravity, about time, and about the nature of reality itself. If you fell into one of these places, what you would actually see, what you would actually feel in the final moments of your fall, would be almost nothing like the violent, screaming, crushing death that films and stories have trained you to imagine. The truth is stranger, the truth is quieter, and in some ways the truth is far more disturbing than any story ever invented. Tonight we are going to fall in together. We are going to follow the journey down, past the point of no return, all the way to the place where the laws of physics themselves stop making sense. We will move slowly, we will take our time, and we will let the strangest ideas in all of science unfold one gentle layer at a time. If you enjoy these long, calm journeys to the farthest edges of physics, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. Make yourself warm and comfortable, let your shoulders drop, and let the questions carry you down into the dark. There is no rush here. There is nowhere else you need to be. Let's begin. To understand what you would see falling into a black hole, you first have to understand how strange the very idea of a black hole is, and how long it took even the greatest minds in history to take that idea seriously. The story does not begin with telescopes or spacecraft. It begins with a quiet country clergyman thinking about light by candlelight, more than 200 years ago. In 1783, a man named John Michell sat in the rectory of a small church in the village of Thornhill, in the north of England. Michell was a clergyman by profession, but he was also one of the most gifted scientific thinkers of his age, a man who studied earthquakes and magnetism and the weighing of the planets. On this occasion, he was thinking about gravity and about light. He knew that if you threw a stone upward, it would slow, stop, and fall back down. He knew that to truly escape the pull of the Earth, an object would have to be moving fast enough, at what we now call escape velocity. And then, he asked a question that nobody had ever asked before. What would happen, Michell wondered, if a star were so massive and its gravity so strong that the speed required to escape it was greater than the speed of light? Light, he reasoned, would try to leave the surface, rise a little way, slow down, and fall back, just like the stone. Such a star would be completely invisible. It would still be there, still enormous, still pulling on everything around it, but no light could ever reach us from it. He called these objects dark stars. He wrote his idea down in a letter to his friend Henry Cavendish, and the Royal Society of London recorded it. And then, for the most part, the world forgot about it. A little over a decade later, in 1796, the great French mathematician Pierre-Simon Laplace arrived at almost exactly the same conclusion, entirely on his own. Laplace was one of the towering figures of mathematics, a man who had worked out the stability of the entire solar system. In a book describing the system of the world, He too described the possibility of a body so large and so dense that light could not escape its gravity. He wrote that the largest bodies in the universe might, for this very reason, remain completely unseen. It was a remarkable insight, and it was also, by the standards of its time, almost completely useless. There was no way to test it, there was no way to find such an object, and there was no real understanding of what light truly was or how gravity truly worked. So the idea of the dark star drifted into the margins of science, an elegant curiosity with nowhere to go. For more than a century, almost nothing happened. The dark star waited, and then, at the start of the 20th century, a patent clerk in Switzerland and a small handful of physicists rewrote the entire foundation of physics, and in doing so, they brought the dark star roaring back to life in a form far stranger than Michel or Laplace could ever have imagined. In November of 1915 in Berlin, Albert Einstein completed the work that would become known as the general theory of relativity. This was not a small adjustment to the old physics. It was a complete reimagining of what gravity is. For Isaac Newton, gravity had been a force, a kind of invisible pull reaching across empty space between any two objects. For Einstein, gravity was something else entirely. Gravity was not a force at all. Gravity was the bending of space and time. Massive objects, Einstein realized, warp the very fabric of the universe around them, and what we feel as the pull of gravity is simply matter following the curves and valleys in that fabric. The Earth orbits the Sun not because a rope of force ties them together, but because the Sun has carved a deep well in the shape of space, and the Earth is rolling around the inside of that well. This was a beautiful and terrifying idea, and it came wrapped in a set of equations so difficult that Einstein himself believed it might take years to find exact solutions to them. He was wrong about that, and the man who proved him wrong was working under conditions that almost defy belief. His name was Karl Schwarzschild. He was a brilliant German astronomer, the director of a famous observatory, and a man already respected across Europe for his work. When the First World War broke out, Schwarzschild, though well into middle age, volunteered for the German army. By late 1915 he was stationed on the Russian front, calculating the trajectories of artillery shells in the freezing cold and the mud and the noise of war. And there, in a military camp, in the middle of a war, he read Einstein's brand new theory of gravity. Within weeks, between his duties, he solved the equations that Einstein thought would take years. He found the first exact description of how space and time bend around a single round mass, like a star. Schwarzschild mailed his solution to Einstein in a letter from the front. Einstein was astonished. He presented Schwarzschild's work to the Prussian Academy of Sciences in his colleague's name, but hidden inside that elegant solution was something deeply unsettling, a feature that even Schwarzschild did not fully grasp, and that would haunt physics for decades. The mathematics said that if you could squeeze a mass into a small enough ball, something extraordinary would happen at a particular distance from its center. At that distance, the equations seemed to break down. Time and space appeared to do impossible things. We now call that critical distance the Schwarzschild radius, and the invisible sphere it traces is the event horizon, the point of no return. Karl Schwarzschild never lived to see what his discovery meant. On the Russian front, he contracted a rare and painful autoimmune disease of the skin called pemphigus. He was sent home, but there was no cure. In May of 1916, only a few months after he had solved Einstein's equations in a war trench, Karl Schwarzschild died. He was 42 years old. He had glimpsed the mathematical shadow of the black hole, and then he was gone, decades before anyone would understand what he had actually found. And for those decades, almost nobody believed it was real. Even Einstein did not believe that such objects could truly exist in nature. The strange behavior at the Schwarzschild radius was dismissed as a mathematical illusion, an artifact of the equations rather than a genuine feature of the universe. Surely, the reasoning went, nature would never actually allow matter to collapse so completely. Surely something would stop it. The idea sat in the textbooks as a kind of theoretical ghost, fascinating but unreal, for nearly half a century. And there was good reason to believe that something would stop it. A star, after all, is not a passive ball of matter waiting to collapse. A star is a furnace, a roaring engine of nuclear fusion, fighting gravity every second of its life. Deep in its core, hydrogen is fused into helium, releasing a flood of energy that pushes outward, holding the enormous weight of the star up against the relentless inward pull of its own gravity. For billions of years, this balance holds. The outward push of the fire and the inward pull of the weight stay perfectly matched, and the star shines steadily, a beacon of light and warmth in the dark. But no fire burns forever. Eventually the fuel runs low, the fusion sputters and fails, and when the outward push of the fire finally dies away, there is nothing left to hold up the crushing weight. Gravity, which has waited patiently for the entire life of the star, finally wins. The core collapses inward upon itself, falling, compressing, searching for something, anything, that can stop it. For most stars, something does. As the core is crushed, the electrons within it are squeezed closer and closer together, until they begin to resist, pushing back with a strange quantum pressure that has nothing to do with heat or fire. This pressure can halt the collapse, leaving behind a dense, faintly glowing ember about the size of our Earth, but containing as much mass as our Sun, a single spoonful of which would weigh several tons. We call these objects white dwarfs, and our own Sun will end its life as one, billions of years from now. But there is a limit. In 1930, a brilliant young physicist named Subrahmanyan Chandrasekhar was sailing from his home in India to England to study at the great University of Cambridge. He was just 19 years old, and on that long ocean voyage with little to do but think, he worked out something profound. He calculated that the quantum pressure of the electrons has a breaking point. If the collapsing core is heavier than about 1 4/10 times the mass of our Sun, that pressure simply is not enough. The collapse cannot be stopped. The star must fall further still. When Chandrasekhar presented this idea in England a few years later, one of the most famous astronomers of the age, Sir Arthur Eddington, stood up and ridiculed it in front of the entire room. Eddington could not accept that nature would permit such a thing. Surely, he insisted, there had to be some law that protected the universe from such an absurdity. But Chandrasekhar was right, and Eddington was wrong, and the young man who had worked out the limit on a ship would live to receive the highest honour in science for that very idea, more than 50 years later. So what stops the collapse when a star is too heavy to become a white dwarf? For a while, there is one more barrier. The crushing gravity forces the electrons and protons to merge together into neutrons, until the entire core becomes a single, unimaginably dense ball of neutrons packed shoulder to shoulder. This object is a neutron star, and it is one of the strangest things in all of nature. It is a city-sized sphere, only about a dozen miles across, and yet it carries more mass than our entire Sun. A single sugar cube of its material would weigh as much as all of humanity combined. It can spin hundreds of times every second, sweeping beams of radiation across the cosmos like a lighthouse. When astronomers first detected these regular rhythmic pulses in 1967, picked up by a young researcher named Jocelyn Bell in Cambridge, the signals were so startlingly precise that for a brief moment some wondered whether they might be messages from another civilization. But even the neutron star has a limit. Pile on too much mass, more than roughly 2 or 3 times the weight of our Sun, and even the fierce resistance of the packed neutrons gives way. And now there is nothing left. No fire, no electron pressure, no neutron pressure. Nothing in all of physics that can hold up the weight. The core collapses without end, falling inward past the point of no return, vanishing behind the very horizon that Schwarzschild had described in the trenches of war. The matter does not stop. As far as our equations can tell, it simply keeps falling, crushed smaller and smaller, toward a fate we will confront for ourselves later tonight, when we follow it all the way down. The name that we use today did not even exist for most of that time. The objects were called frozen stars, or collapsed stars, or simply dark stars, the old phrase echoing down from Michel and Laplace. Then, in 1967, at a scientific meeting in New York, the American physicist John Wheeler used a short, blunt, unforgettable phrase to describe these collapsed objects. He called them black holes. The name was perfect. It was dark, it was final, and it captured the imagination instantly. Within a few years, the entire world was using it. A two-word phrase had turned an obscure mathematical curiosity into one of the most famous ideas in all of science. But a good name is not proof. The real question remained: were black holes only equations on a chalkboard, or were they actually out there, lurking in the dark between the stars? The answer began to arrive through an entirely new kind of astronomy. An astronomy not of visible light, but of invisible X-rays pouring down from the sky. In the early 1960s, instruments lifted above the atmosphere began detecting powerful sources of X-rays scattered across the heavens. One of the strongest sat in the constellation of Cygnus, the Swan, and it was given the name Cygnus X1. As astronomers studied it through the late 1960s and into the 1970s, they pieced together a disturbing picture. There was a large, bright, ordinary star there, and it was orbiting something it could not see, something heavy enough to whip that giant star around in a tight, fast circle, and yet small enough and dark enough to give off no visible light at all. The invisible companion was far too massive to be a dead star of any ordinary kind. The only explanation that fit the mathematics was a black hole, perhaps 20 times the mass of our Sun, crushed into a region only a few miles across, tearing gas off its companion and heating it until it screamed in X-rays as it fell to its doom. That screaming of the gas is worth pausing on, because it reveals one of the great ironies of these objects. A black hole itself gives off no light at all. It is the darkest thing in the universe, and yet the regions immediately around a feeding black hole can blaze brighter than almost anything else in all of creation. The reason lies in how matter falls in. Gas and dust drawn toward a black hole almost never plunge straight down. Instead, like water circling a drain, they spiral inward, swirling around and around, forming a vast flattened disk of doomed material that we call an accretion disk. As this gas spirals closer, it is squeezed and sheared, the inner edge racing around far faster than the outer edge, the layers grinding against one another with unimaginable friction. That friction heats the gas to staggering temperatures, to millions of degrees, until the entire disk glows white hot and pours out radiation across every wavelength, from radio waves to visible light to fierce X-rays. The darkest thing that exists dresses itself in a robe of brilliant fire, and the fire can be astonishing. When a truly enormous black hole, millions or billions of times the mass of our Sun, feeds at the center of a galaxy, the disk around it can shine more brightly than every star in that galaxy combined. We see these blazing cores scattered across the most distant reaches of the universe, so bright that we mistook them at first for ordinary stars, and so we gave them a strange name, quasars, a word meaning star-like. In 1963, an astronomer named Martin Schmidt realized that one of these faint points of light was not a star at all, but the incandescent heart of a galaxy, billions of light years away, outshining 1 trillion suns, powered by matter falling into a supermassive black hole. Some of the brightest quasars we have ever found are so luminous that we can see them across nearly the entire observable universe, their light reaching us from a time when the cosmos itself was young, beacons lit by the act of destruction itself. There is a strange efficiency hidden in this. When you burn wood in a fire, or even when a star fuses hydrogen in its core, only a tiny fraction of the available energy is released, less than 1 part in 100 of the mass becoming light. But matter falling toward a black hole, spiraling down through that superheated disk, can release a far greater share, in some cases approaching 1/10 or more of its entire mass, converted into pure energy before it ever crosses the edge. Pound for pound, feeding a black hole is among the most efficient ways the universe has of turning matter into light. The darkest objects in creation are also, in their hunger, the brightest engines that exist. But the disk cannot extend all the way inward. There is a point, a little way outside the event horizon, beyond which no stable orbit is possible, where gravity grows so steep that anything circling must finally let go and spiral in. The gas makes its last few loops there, glowing its hottest and most furious, and then slips over the edge into silence. It is the final brilliant scream of matter before the dark takes it. This will matter for our own journey, because the giant we have chosen to fall toward, the black hole at the center of our own galaxy, is not feeding now. It is quiet, starved, and dim. Its disk is faint, its fire banked low, and so our descent, when we begin it in earnest, will not be a plunge into blinding light. It will be a fall through darkness and silence toward a sphere of perfect black. Had we chosen a feeding monster instead, the approach would have been very different. A descent through a storm of radiation that would have unmade us long before the edge. We have chosen the quiet giant for a reason. It will let us fall in peace. So confident was this conclusion becoming, that two of the most famous physicists in the world made a wager about it. Stephen Hawking and Kip Thorne placed a bet on whether Cygnus X1 truly contained a black hole. Hawking, strangely, bet that it did not, and he later explained that this was a kind of insurance. He had spent his life studying black holes, and if they turned out not to exist, at least he would win the bet as a consolation. As the years passed and the evidence piled higher and higher, Hawking eventually conceded. The bet was settled. The smart money, and then all the money, was on the black hole being real. As the years passed, the evidence grew from a handful of strange X-ray sources into something overwhelming, and nowhere more so than at the very center of our own galaxy. Beginning in the early 1990s, two teams of astronomers, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in California, began doing something that sounds almost impossible. They began watching individual stars near the heart of the Milky Way, tracking their motion year after year patiently for decades. What they saw was extraordinary. The stars at the galactic center were not drifting lazily through space. They were racing, whipping around an invisible point along enormous looping orbits, flung about by the gravity of something they could not see. One star in particular swung around on a tight, fast orbit, completing a full loop in about 16 years, and at its closest approach it was traveling at thousands of miles every second, a small but real fraction of the speed of light itself. To bend the path of a star that violently, to fling it around that fast, required an object of staggering mass, crammed into an astonishingly small space. When the astronomers did the arithmetic, the answer was undeniable. Sitting at the center of our galaxy, in a region smaller than our own solar system, was something with the mass of about 4 million suns. There is only one thing in all of physics that can pack 4 million times the mass of our sun into a space that small and emit almost no light at all. It had to be a supermassive black hole. We could not see it, but we could see the stars dancing around it, held in their wild orbits by its invisible grip, and from their dance we could weigh the darkness at the center of our home. This patient, decades-long watch became some of the most powerful evidence ever gathered that black holes are real. In the year 2020, Reinhard Genzel and Andrea Ghez were awarded the highest honor in physics for this work, sharing it with Roger Penrose, whose mathematics had shown decades earlier that such collapse was not only possible, but, under the right conditions, inevitable. Andrea Ghez became only the fourth woman in history to receive that honor in physics. Together, their work turned the black hole from a strong suspicion into an established fact of nature, a monster proven to be sitting, right now, some 26,000 light-years away, at the very center of the galaxy we call home. Still, all of this was indirect. We were measuring the orbits of stars, watching the glow of doomed gas, inferring the presence of something we could never actually see. For most of human history, the black hole remained a shadow, a thing known only by its effects, never by its face. And then, after more than 2 centuries of imagining, humanity finally did something that Michel and Laplace and Schwarzschild could only have dreamed of. We took its picture. On the 10th of April, 2019, an international team running a project called the Event Horizon Telescope released the first photograph ever taken of a black hole. To capture it, they had linked together radio telescopes scattered all across the planet, from Hawaii to Spain to the South Pole, turning the entire Earth into a single enormous eye. Their target was the monstrous black hole at the heart of a distant galaxy called Messier 87, an object 6.5 billion times the mass of our Sun, sitting roughly 55 million light-years away. The image showed a ring of glowing gas, bright and fierce, wrapped around a perfect circle of absolute darkness. That darkness was the shadow of the event horizon. It was the silhouette of a region from which no light returns. For the first time in history, we were looking directly at the edge of one of these things. A few years later, in 2022, the same team unveiled a second portrait, and this one was far closer to home. They had photographed the black hole at the center of our own galaxy, the Milky Way, an object named Sagittarius A star, sitting about 26,000 light-years from where you are right now. It is more than 4 million times the mass of our Sun, and it has been there, quietly anchoring the entire rotation of our galaxy for billions of years. Every star you have ever seen in the night sky, including our own Sun, is circling slowly around it. Think about what that journey of discovery really means. For more than 2 centuries, the black hole was only an idea, a frightening possibility hiding inside the mathematics, dismissed by Einstein himself as something too strange to be real. And then we built a telescope the size of the Earth, and we pointed it into the dark, and there it was. The monster was real. It had a face after all, and it had been waiting at the very center of our own galaxy the entire time. The question is no longer whether these places exist. The question is, what would happen to you, in the quiet and the dark, if you ever fell into one? To fall into a black hole, you first have to reach its edge. And to understand that edge, we need to understand the single most important idea in this entire story. That idea is the event horizon. Almost everything strange about black holes flows from this one concept, and almost everything that people believe about it is slightly wrong. So let us build it slowly, from the ground up, starting with something simple that you already know in your body. Throw a ball into the air. It rises, it slows, it stops, and it falls back into your hand. Throw it harder, and it rises higher before returning. The harder you throw, the higher it climbs. Now imagine you could throw it impossibly hard. There exists a particular speed, a magic threshold, at which the ball would rise and never come back. It would coast upward forever, slowly slowing, but never quite stopping, escaping the Earth entirely. That threshold has a name. We call it escape velocity. For our planet, the escape velocity is about 25,000 miles per hour. Launch anything faster than that, straight up, and it will leave the Earth behind and never fall back. Escape velocity depends on 2 things, and only 2 things. It depends on how much mass an object has, and on how close you are to its center. More mass means a stronger pull and a higher escape velocity. Getting closer to the center also means a stronger pull and a higher escape velocity. This is the key. If you could somehow stand closer and closer to the center of a heavy object, the speed you would need to escape would climb higher and higher. Now we can ask the question that started everything, the same question that John Michel asked by candlelight more than 200 years ago. What if you crushed an object so small and packed its mass so tightly that the escape velocity at its surface reached the speed of light? At that point, light itself could no longer escape, and because nothing can travel faster than light, nothing else could escape either. You would have created a region of space with a one-way door. Things could fall in, nothing could ever climb back out. The distance from the center at which the escape velocity reaches the speed of light is the Schwarzschild radius, named for the dying astronomer who first calculated it in a war trench. The imaginary sphere at that distance is the event horizon. It is not a solid surface. It is not a wall. There is nothing there to touch, nothing there to see, no shimmering membrane hanging in space. The event horizon is simply a boundary, a mathematical line in the emptiness that marks the place where the escape velocity finally crosses the speed of light. On one side, escape is still possible, however difficult. On the other side, escape is no longer a question of effort. It is a question of geometry, and the geometry says no. Consider how small you would have to crush things to reach this threshold, because the numbers are genuinely shocking. To turn our own sun into a black hole, you would have to compress all of its mass, all of those 900 billion tons of blazing gas, down into a ball only about 2 miles in radius. The entire sun, an object well over 800,000 miles wide, squeezed into a sphere you could walk across in an hour. To turn the Earth into a black hole, you would have to crush our entire planet, all of its oceans and mountains and molten core, down into a ball smaller than a marble. Everything you have ever known, every city and continent, compressed to the size of something you could hold between 2 fingers. That is how absurdly dense a black hole truly is. It is not a big object. It is the most compact thing the universe can make. This distinction matters enormously because it reveals one of the most stubborn and widespread misconceptions about black holes, a belief so common that almost everyone carries it without ever questioning it. Ask most people what a black hole does, and they will tell you that it sucks things in. They picture a cosmic vacuum cleaner, a drain in the fabric of space, reaching out across the galaxy to swallow everything around it. They imagine that if a black hole appeared in our solar system, the Earth and all the planets would immediately be dragged screaming into oblivion. That confident picture is wrong. Not slightly wrong. Fundamentally wrong. A black hole does not suck. A black hole has gravity, ordinary gravity, the same gravity that any object with mass possesses. And gravity, despite its fearsome reputation, follows the same gentle rules whether it comes from a planet, a star, or a black hole. Here is the truth that almost nobody expects. If you replaced our sun, right now, with a black hole of exactly the same mass, the Earth would not be sucked in. The Earth would not even notice. It would continue circling in precisely the same orbit it follows today, at precisely the same distance, for billions of years. The only thing that would change is the light. The sky would go dark, and the cold would come, but the gravity would be identical. From a safe distance, a black hole pulls on you no harder than any other object of the same mass. It is only when you come close, terribly close, far closer than the original star ever allowed, that gravity begins to do the things that make black holes so feared. This is why the event horizon is so important and so deceptive. The danger of a black hole is not that it reaches out to grab you. The danger is that it lets you get close. A normal star has a surface. You can only approach the sun so far before you slam into its blazing outer layers, hundreds of thousands of miles from its center, where the escape velocity is still a tiny fraction of the speed of light. The sun simply will not let you get close enough for its gravity to become a trap. A black hole, by contrast, has no surface to stop you. All of its mass is hidden far below the event horizon, crushed into a vanishing point. So you can fall closer, and closer, and closer, sliding inward through empty space, with nothing to block your path, until you reach that invisible line where the escape velocity finally exceeds the speed of light. And by the time you cross it, it is already too late. The size of the event horizon depends entirely on the mass of the black hole, and the range is staggering. The black hole that Cygnus X1 harbors, around 20 times the mass of our Sun, has an event horizon only about 40 miles across. You could drive across it in less than an hour if driving across such a thing were possible, which it is not. The black hole at the center of our galaxy, Sagittarius A star, with its 4 million solar masses, has an event horizon roughly 17 times wider than the Sun itself, a dark sphere large enough to swallow the orbit of the planet Mercury. And the giant in the galaxy Messier 87, the first black hole ever photographed, is so enormous that its event horizon stretches wider than the orbit of Neptune. Its dark boundary is larger than our entire solar system. Our Sun, all of the planets, and everything out to the farthest icy worlds would fit comfortably inside that single sphere of darkness, with room to spare. It is worth taking a moment to absorb the sheer range of these objects, because they come in sizes that span an almost unimaginable spectrum. At the smaller end are the stellar black holes, the corpses of individual massive stars that collapsed at the ends of their lives. These typically carry somewhere between a few times and a few dozen times the mass of our Sun, packed into a sphere only miles across. They are scattered throughout every galaxy, the dark remnants of stars that died long ago. Our own Milky Way is thought to contain many millions of them, drifting silently between the stars, almost all of them invisible, betraying their presence only on the rare occasions when they feed or collide. At the other extreme are the supermassive black holes, the titans that sit at the centers of galaxies. These are not the corpses of single stars. They carry the mass of millions or even billions of suns. The one at the center of our own galaxy weighs about 4 million suns, which sounds enormous until you set it beside the giant in the galaxy Messier 87, which weighs more than 6 billion. And even that is not the largest. In the depths of the distant universe, astronomers have found monsters of truly absurd scale, one of them weighing some 66 billion times the mass of our Sun, a single object more massive than many entire dwarf galaxies. How such giants grew so large, and especially how they grew so quickly, remains one of the deepest unsolved puzzles in all of astronomy. We find fully formed supermassive black holes already blazing as quasars when the universe was still very young. Far too young, it seems, for them to have grown so vast by swallowing matter one slow mouthful at a time. Something about their birth we simply do not yet understand. Between these two extremes lies a strange and sparsely populated middle ground, the intermediate black holes, weighing hundreds or thousands of suns. For a long time these were almost entirely missing from our surveys, a curious gap in the family, though in recent years a handful of candidates have begun to fill it in. And at the very smallest end, there is a stranger possibility still. Some physicists suspect that in the violent chaos of the first instance after the birth of the universe, tiny black holes may have formed directly out of the dense, churning matter of the infant cosmos. We call them primordial black holes, and some may be no heavier than a mountain, others no larger across than a single atom, yet carrying the mass of an asteroid. Whether any of these tiny ancient relics still drift, unseen, through the dark today, nobody yet knows. They remain a tantalizing possibility, hunted for but never confirmed. What unites all of them, from the smallest primordial speck to the most monstrous quasar, is the same simple, terrible rule. Each one has an event horizon, a radius of no return, set by its mass and nothing else. Each one is a place where the escape velocity has reached the speed of light, and each one, large or small, ancient or newborn, hides the same impossible mystery at its heart. The black hole we will fall into tonight is only one member of this vast and shadowy family, but what we learn by falling into it is true of them all. To appreciate how strange this truly is, consider what the event horizon actually represents. It is not made of anything. If you were falling toward a large black hole, you would not see the event horizon as a glowing line or a dark wall ahead of you. You would see perhaps a circle of blackness against the stars, growing larger as you approached, surrounded by a ring of distorted, smeared light from everything behind it. But the horizon itself is invisible. There would be no warning sign, no sudden jolt, no sound, no flash, no sensation at all to tell you the precise moment you crossed it. You could pass through the most important boundary in the universe, the place beyond which return is forever impossible, and feel absolutely nothing. One moment you are in a universe where escape is still theoretically possible. The next moment you are in a universe where it is not. And nothing in your body, nothing in your eyes, nothing in the space around you would mark the transition. This is the quiet horror at the heart of the black hole. The trap does not announce itself. It does not warn you. The most consequential line you could ever cross is utterly silent, utterly invisible, and absolutely final. By the time any signal could tell you that you had crossed it, that signal would already be falling inward alongside you, unable to climb back out and warn the rest of the universe what had become of you. So the event horizon is not a thing. It is a place where the rules change. It is the boundary between the part of the universe that can still send light to the stars and the part that has been severed from the rest of reality forever. Everything inside that sphere has, in a very real sense, left our universe. It can still pull on us with its gravity. It can still bend the light that passes nearby, but it can never again send us a single photon, a single particle, a single whisper of information about what lies within. It has become a one-way door, and the door only opens inward. And now comes the question that will carry us deeper into the dark. If you crossed that silent, invisible line, what would happen to your body? What would the journey down actually feel like? The answer depends, in a way that almost no one expects, on one simple thing. Not on how dangerous the black hole is, but on how large it is. And the larger the black hole, the gentler and stranger the fall. Let us begin the fall. Imagine that you are drifting in space, far from any star, and below you waits a black hole. You have decided, for reasons that belong only to you, to fall in. You orient yourself feet first, and you let go, and you begin to drop. At first, nothing dramatic happens. You are simply falling, weightless, the way an astronaut falls endlessly around the Earth. The black hole is still far away, a dark coin against the field of stars. And here, far out, its gravity behaves like the gravity of any ordinary object. It pulls you gently toward it, and you accelerate, faster and faster, sliding inward through the dark. But gravity has a subtle and deadly property, one that we rarely notice in ordinary life, because the objects around us are too small and too far away. Gravity is not the same everywhere. It is stronger when you are closer to the source, and weaker when you are farther away. This means that as you fall feet first toward the black hole, your feet, being slightly closer to it, feel a slightly stronger pull than your head. The difference is tiny at first, almost nothing. But it is there. Your feet are being pulled down a little harder than your head, and so, very gently, you begin to stretch. This stretching effect has a name in physics. It is called the tidal force, and it is the same effect that raises the oceans on our own world. The moon pulls a little harder on the side of the Earth facing it than on the far side, and that difference in pull stretches the oceans into a bulge, giving us the tides. The tidal force is not about how strong gravity is overall. It is about how quickly gravity changes from one point to another, and near a black hole, gravity can change with terrifying speed across very short distances. Stephen Hawking gave the result of this stretching a darkly playful name. He called it spaghettification. As you fall closer and closer to a black hole, the difference in pull between your feet and your head grows larger and larger. You are stretched longer and thinner, drawn out like a strand of pasta, while at the same time you are squeezed inward from the sides, because every part of you is being pulled toward the same central point. You become a long, thin thread of matter, falling toward your doom. And eventually, if the tidal forces grow strong enough, you are torn apart. First your body, then your cells, then your molecules, then your very atoms, pulled into a stream of particles plunging into the dark. This is not merely a theoretical fate dreamed up by physicists. Astronomers have actually watched it happen, on a scale far larger than any human body. Every so often, a star in a distant galaxy wanders too close to the supermassive black hole at its center. When it crosses a certain threshold, The tidal forces of the black hole overwhelm the star's own gravity, the force that normally holds it together as a sphere. The star is stretched, then torn apart, spaghettified across the sky, ripped into a long ribbon of glowing gas. Roughly half of that shredded material is flung back out into space. The other half spirals inward toward the black hole, heating to enormous temperatures as it falls, and erupts in a brilliant flare of light that can briefly outshine all the billions of stars in its galaxy combined. We call these events tidal disruptions, and modern sky surveys, which scan the heavens night after night for anything that changes, have now caught dozens of them in the act. We have watched, from across hundreds of millions of light years, the precise moment a star was unmade by a black hole, brightening over weeks and then slowly fading over months and years as the last of the star drained away into the dark. Spaghettification is real. We have the photographs of its aftermath, written in light across the universe. Here is where the story takes its most surprising turn. The fact that overturns everything our intuition tells us. You might assume that the bigger the black hole, the more violent and more deadly the fall. A larger black hole has more mass after all, and more mass means stronger gravity. But the tidal force, the stretching that kills you, does not depend on mass in the simple way you would expect. It depends on how sharply gravity changes across the small span of your body. And around a small black hole, gravity changes incredibly sharply, because all of that mass is packed into a tiny region, and the event horizon sits very close to the lethal center. Around a giant black hole, the mass is so vast, and the event horizon so enormous, that you can cross the boundary while still being relatively far from the deadly center, in a region where gravity, though immense, changes only gradually from your head to your feet. Consider what this means. If you fell toward a black hole of only a few times the mass of our Sun, like the one in Cygnus X1, you would be killed long before you ever reached the event horizon. The tidal forces would become lethal while you are still hundreds of miles outside the boundary. You would be stretched and torn apart in the open, ripped into a glowing stream of particles, and what remained of you would cross the horizon as a thin spray of atoms. The fall into a small black hole is exactly as violent as the stories suggest. You would never even reach the edge as anything resembling yourself. But the fall into a giant black hole is something else entirely, and this is where the deepest strangeness begins. If you fell towards Sagittarius A star, the 4 million solar mass black hole at the center of our own galaxy, the tidal forces at the event horizon would be astonishingly gentle. So gentle that you might not feel them at all. You could cross the event horizon, the most absolute boundary in the universe, the line beyond which return is forever impossible, while feeling perfectly intact, perfectly whole, perfectly comfortable. Your body would not be stretched, your atoms would not be torn. You would simply continue falling, alive and aware, into a region from which you could never return, with no physical sensation whatsoever to tell you that the most important thing that would ever happen to you had just happened. And for the truly enormous black holes, the giants like the one in Messier 87, the crossing would be gentler still. You could pass through that event horizon, a boundary larger than our entire solar system, as easily as you might drift through an open doorway in the dark. There would be no resistance, no barrier, no moment of impact. Just the silent, weightless continuation of your fall, deeper into a place from which the universe will never hear from you again. This is the trap, and it is far crueler than any vacuum cleaner pulling you in. The largest, most monstrous black holes in the universe are the ones that let you cross their thresholds peacefully, painlessly, without warning. The gentleness is not mercy, it is deception. A small black hole at least gives you a violent, unmistakable end, a fate you can see coming as the tidal forces build. A giant black hole lets you slip across the point of no return in complete comfort, fully alive, fully conscious, while the door closes silently behind you forever. The horror is not the pain, the horror is the calm. So let us choose the giant. Let us choose to fall, not into a small and violent black hole that would tear us apart in the open, but into Sagittarius A star, the great black hole at the heart of our galaxy, where the crossing is gentle and where we will survive long enough to actually see what lies beyond the edge. We orient ourselves and we fall, and the dark sphere below us grows. It swells from a coin to a plate to a vast wall of absolute blackness, blotting out more and more of the stars. Around the edge of that darkness, the light of the universe behind us begins to bend and smear into a brilliant, distorted ring. We are approaching the event horizon, and we are still alive, still whole, still watching. But before we cross that final boundary, something even stranger is about to happen. Something that has nothing to do with our bodies and everything to do with time itself. Because as we fall toward the event horizon, the way that we experience time and the way that the rest of the universe experiences our fall begin to separate from each other. Not slightly, not as a small correction. They begin to diverge so completely that to an observer watching from a safe distance, we will never actually fall in at all. And to us, falling, the entire future of the universe will begin to unfold in the sky above. To appreciate how disturbing this is, you have to abandon one of the most basic assumptions you carry through every moment of your life. You assume that time is universal. You assume that a second is a second, the same for everyone, everywhere, always ticking forward at the same steady rate. You assume that if two people start their stopwatches together, those watches will always agree. This assumption feels so obvious, so unquestionable, that it seems absurd to even state it. And it is wrong. It has been proven wrong in laboratories with real clocks again and again. Time is not universal. Time bends. Time stretches and slows. And near the event horizon of a black hole, time does something so extreme that it severs our fall from the rest of reality entirely. This is the next layer of the descent, and it is the strangest one yet. We have crossed from the world of bodies and tides into the world of time itself, where the very meaning of when and now begins to dissolve. Hold on to that one simple idea as we go deeper. Time is not the same for everyone, and near a black hole, that difference becomes everything. The idea that time can slow down sounds like fantasy, like something invented for a film, but it is one of the most thoroughly tested facts in all of science, confirmed not once but thousands of times, with clocks so precise that they can measure the slowing of time across the height of a single staircase. To understand what happens to us as we fall, we have to first understand how time truly behaves, and the proof comes not from black holes, but from ordinary clocks carried in ordinary places here on Earth. In 1971, two scientists named Joseph Hafele and Richard Keating performed an experiment so simple in concept that it sounds almost like a joke. They took several extremely precise atomic clocks, the most accurate timekeepers ever built, and they bought airline tickets. They flew the clocks around the world on ordinary commercial flights, once heading east, once heading west, while identical clocks stayed behind on the ground. Einstein's theories made a clear prediction. Because of their motion and because of their altitude, where the Earth's gravity is slightly weaker, the flying clocks should end their journey reading a slightly different time than the clocks that stayed home. When the planes landed, the scientists compared the clocks. The difference was tiny, measured in billionths of a second, and it matched Einstein's prediction almost exactly. Time had genuinely flowed at a different rate for the clocks that flew. This is not a rare or exotic effect. It is happening constantly, all around you, all the time. The satellites of the Global Positioning System, the constellation of spacecraft that lets your phone know exactly where you are, orbit high above the Earth where gravity is weaker. Up there, their clocks run faster than clocks on the ground, gaining about 38 millionths of a second every single day. That sounds utterly trivial, but if the system did not correct for it, the errors would pile up so quickly that within a single day your navigation would be wrong by several miles. Every time you use a map on your phone, you are relying on engineers having accounted for the fact that time runs at different speeds at different heights. The bending of time is not a curiosity. It is built into the technology in your pocket. The deeper truth, the one Einstein revealed in his general theory of relativity, is this. Clocks run slower in stronger gravity. The deeper you sit inside a gravitational well, the more slowly your time flows compared to someone higher up. On the surface of the Earth, where gravity is mild, this effect is almost imperceptible. But near the event horizon of a black hole, where gravity becomes nearly infinite, the effect becomes overwhelming. And this is the key that unlocks the strangest part of the entire fall. Picture two of us now. One person falls towards Sagittarius A star, dropping toward the event horizon. The other stays behind, hovering at a safe distance, watching through a powerful telescope. As the faller drops closer and closer to the horizon, sinking deeper into that monstrous well of gravity, their time runs slower and slower compared to the distant watcher. And from the watcher's point of view, something deeply unsettling begins to unfold. The falling figure appears to slow down, not because they are decelerating, but because their time is stretching. Every movement becomes sluggish, dreamlike, drawn out. The light coming from them begins to shift, its color sliding from white toward red and then toward deep, dim red, because the light itself is losing energy as it climbs out of the gravitational well. This reddening has been measured directly here on Earth. In 1959, two physicists named Robert Pound and Glenn Rebka stood at the top and bottom of a tower at Harvard University and measured light losing exactly this kind of energy as it rose just a few dozen feet against Earth's gravity. Near a black hole, the same effect becomes extreme beyond imagining. As the faller approaches the horizon, the watcher sees them grow redder and dimmer and slower still. The falling figure seems to freeze, hanging just above the event horizon, fading toward invisibility but never quite vanishing, never quite crossing. To the distant observer, the faller never reaches the horizon at all. They simply slow to a stop, redshift into darkness, and become a faint frozen image smeared across the edge of the black hole, growing fainter for all eternity but never ever falling in. Sit with that image for a moment, because there is a quiet human horror folded inside it. Imagine the two of us again, one falling, one staying behind to watch. Imagine that as you fall, you carry a small light, and once every second by your own watch you flash it back toward your friend. A steady signal that says, I am still here, I am still falling, I am still alive. At first your friend receives the flashes just as you send them, one every second, calm and regular. But as you sink closer to the horizon, the flashes begin to arrive farther and farther apart. Not because you are sending them more slowly. By your own watch, you are flashing exactly once a second, as steadily as ever. But the light climbing back out of that deepening gravity takes longer and longer to escape. And so, to your friend, your signal slows. One flash every second becomes one every 2 seconds, then one every 10, then one every hour, then one every year. Each flash arrives dimmer than the last, its light drained of energy by the long climb out, reddening from white to orange to deep red, and onward into colors the eye can no longer see. Your friend would watch your signal slow and redden and fade, the intervals stretching toward forever, the light guttering down toward darkness. And then, in principle, the flashes would simply never quite stop. They would grow so faint and so far apart that they faded below anything that could ever be detected. A final dim ember of a message strung out across the rest of eternity. And here is the cruelty hidden in the mathematics. While your image hangs there, frozen and fading at the edge, the universe your friend lives in would carry on. Your friend could grow old and grey, waiting for a crossing that to them never comes. Whole human lifetimes could pass. The stars overhead could drift into new patterns, and still, faintly, impossibly, that last reddening image of you would remain, pinned to the threshold of the dark, a photograph the universe refuses to finish developing. This is so strange and so counterintuitive that the early Russian physicists who studied black holes gave them a name based entirely on this effect. They did not call them black holes. They called them frozen stars, because from the outside, that is exactly what they appear to be. Anything falling toward them appears to freeze at the edge, locked in time, hovering forever at the threshold, an image that fades but never completes its fall. But here is the part that breaks the mind in half. None of that is what the faller experiences. From the falling person's own point of view, nothing strange happens to time at all. Their watch keeps ticking normally. Their thoughts run at their usual speed. They do not feel themselves slowing down, because relative to themselves they are not slowing down. They simply fall, smoothly and steadily, toward the dark sphere below. And then, at a perfectly ordinary moment, with no fanfare and no sensation, they cross the event horizon. For them, the crossing takes a finite, measurable, entirely normal amount of time. They fall right through the boundary that, to the outside universe, they could never reach. So which is true? Does the faller cross the horizon, or do they freeze forever at the edge? The astonishing answer is that both are true, each from its own point of view, and there is no contradiction. The distant observer genuinely never sees the fall across, because the light carrying that final image takes longer and longer to climb out, stretching toward infinity. The faller genuinely does cross, in a finite time, by their own reckoning. Time has not just slowed. The very notion of a single, shared, universal now has dissolved completely. There is the faller's now, and there is the watcher's now. And near a black hole, these two nows part ways forever and never meet again. This brings us to one of the most beloved and most misunderstood ideas about falling into a black hole, a claim you may have heard before. People often say that as you fall in, you would see the entire future of the universe play out above you, the stars aging, the galaxies dying, the whole of cosmic history racing by in your final moments. It is a beautiful, haunting idea, and for someone falling freely into the black hole, it is not actually true. Here is the subtlety that almost everyone misses. The vision of the universe's entire future racing by belongs to a different kind of observer, one who hovers just outside the horizon, firing powerful rockets to hold their position against the crushing gravity, refusing to fall. Such a hovering observer, fighting to stay still right at the edge, would indeed see the outside universe sped up dramatically, the future rushing toward them. But a person who simply lets go and falls freely does not hover. They plunge through the horizon in a finite time, far too quickly to watch eternity unfold. They would see the outside universe distorted and brightened and blue-shifted. Yes, but they would not witness the death of the cosmos. They would cross the threshold while the universe outside was still young, still familiar, still recognizably the same age as the moment they jumped. The myth confuses the one who falls with the one who refuses to fall. And that difference, the difference between letting go and holding on, changes everything about what you would actually see. So what would you truly see, falling freely towards Sagittarius A star? As you drop toward the event horizon, the dark sphere swelling beneath you, the entire sky would begin to warp. The black hole's gravity bends the paths of light passing nearby, acting like a colossal lens. The stars behind the black hole, whose light would normally be blocked, are bent around its edges and brought into view, smeared into a brilliant, shifting ring of light wrapped around the darkness. The whole universe behind you would appear to crowd together, squeezed and concentrated into a shrinking circle of light above you, growing smaller and brighter and bluer as you fall. The blackness would expand to fill more and more of your view, until the entire universe, every star and galaxy you had ever known, was compressed into a single bright, distorted window overhead, growing smaller as you sank away from it. It would be silent, it would be beautiful, and it would be the last thing you would ever see of the world you came from. But let us slow down and return for a moment to the approach, because we have rushed past the most beautiful sight in the entire descent. Before you reach the event horizon, you pass through a region with a strange and wonderful property, a place where light itself can be trapped in orbit. It sits at a distance of 1.5 times the radius of the event horizon, and we call it the photon sphere. Here, gravity bends the path of light so severely that a beam of light can travel in a perfect circle, looping around and around the black hole, orbiting it the way a planet orbits a star. Light, the fastest and straightest thing in the universe, is bent into a ring. Consider what this means for what you would see. If you could pause at the photon sphere and look out to the side, along the direction of that orbit, the light leaving the back of your own head could travel all the way around the black hole and come back to your eyes from the front. You would see the back of your own head, floating in the distance, wrapped around the darkness. You would see yourself, reflected not in any mirror, but in the bending of space itself. It is one of the strangest sights the universe permits, and it exists at the edge of every black hole, waiting for an eye that will never come. This same bending of light is what gives black holes their haunting appearance in the photographs we have taken. The bright ring of light that surrounds the dark center is not simply the glow of nearby gas. Part of that ring is made of light that has looped around the black hole one or more times before escaping toward us. Light that has circled the darkness and survived to tell of it. We call it the photon ring, and it is the fingerprint of the most extreme light bending in nature. The Event Horizon Telescope, that planet-sized eye we built, was designed in part to capture exactly this delicate ring of looping light. There is another consequence, subtle and disturbing. The black sphere you would see, the silhouette of the darkness, is actually larger than the true event horizon. The black hole bends the light coming from behind it, sweeping it around its edges and into your view, and this makes the shadow appear swollen, roughly 2.5 times wider than the horizon truly is. The darkness you would see is bigger than the darkness that is really there. The black hole casts a shadow larger than itself, an exaggeration written into the geometry of space, a void that looks even more total than it already is. And the bending does not stop at simple reflection. The black hole acts as a colossal lens, gathering the light of everything behind it and warping it into arcs and rings and duplicate images. A single star sitting directly behind the black hole would not appear as a single point. Its light would be bent around every side at once, smeared into a perfect circle of light surrounding the darkness, a halo with no source you could point to. The entire sky behind the black hole would be stretched and curved and multiplied, every object appearing in several places at once, the whole universe behind you wrapped and folded around the edge of the dark. This is what you would truly see in the final approach. Not a simple black ball against the stars, but a churning, shifting lens of light, the cosmos itself bent into rings around a hole in the world. And there is one more strange gift the bending of light would give you, if you could watch carefully enough on the way down. Look outward, away from the black hole, toward the distant universe you are leaving behind. Because of the way the black hole's gravity and your own headlong fall conspire together, the light arriving from the outside cosmos would be shifted toward the blue, gathered and concentrated and brightened, as though the universe were leaning in to watch you go. The stars would not only crowd together into that shining ring above you, they would appear to burn hotter and whiter, their light squeezed toward higher energies, the whole sky sharpening into a fierce and brilliant crown, and the universe out there would appear to hurry. Just as a distant observer would see your clock slow to a crawl, you, falling inward, would see their clocks racing. The slow turning of distant stars, the patient drift of far galaxies, all of it would appear to speed up, the outside cosmos playing forward faster and faster as you fell, time itself seeming to accelerate beyond the edge of the world you were leaving. It would be like watching a film of the universe set running at ever-increasing speed, glimpsed through a shrinking window of brilliant gathered light. Look toward the bright ring of trapped light itself, and you would see something stranger still. The light there has not traveled to you in a simple straight line. Some of it has curved halfway around the black hole before reaching your eyes. Some of it has looped fully around once, or twice or more. And so within that ring you would see the universe repeated, layered, echoed, the same stars appearing again and again, in ever thinner copies, an endless series of fainter and fainter images of the entire sky, stacked at the very lip of the darkness. You would be looking at light that had circled a black hole to reach you, carrying ghostly duplicate images of the cosmos behind your own back. And below you, where the black hole waited, there would be nothing. Not darkness in the ordinary sense, not the soft black of a night sky scattered with distant suns, but a true and total absence, a perfect circle of nothing that grew and grew until it swallowed half of everything you could see, then more than half, the floor of the universe opening beneath you into a pit with no bottom and no light. There would be no sense of speed, no wind, no roar, only the silent swelling dark below, the gathering brilliance above, and the strange calm certainty that you were falling toward a place from which the word return had been quietly erased. We have now followed the fall to the very edge. We have watched time itself split into two irreconcilable stories. We have seen the universe shrink to a single point of light above us, and we are about to do the one thing that no human being and no signal has ever done and returned to describe. We are about to cross the event horizon and ask the final question. What is on the other side? What happens after you pass the point of no return? The answer is the strangest idea in this entire journey, because beyond the horizon, the meaning of the words here and now, of space and time themselves, turns completely inside out. We cross the event horizon. There is no sound, no flash, no jolt, no sensation of any kind. The ring of bright, distorted light still hangs above us, the last image of the universe we left behind, shrinking slowly toward a point. We are alive. We are whole. By every measure our body can detect, nothing has changed. And yet everything has changed, in a way so profound that it overturns the very meaning of space and time. Because inside the event horizon of a black hole, space and time exchange their roles. To understand this, hold on to one ordinary fact about your everyday life. You can move freely through space. You can walk forward or backward, left or right, up or down. You choose your direction in space. But you cannot choose your direction in time. Time carries you forward, always, relentlessly, whether you like it or not. You cannot stop tomorrow from coming. You cannot turn around and walk back into yesterday. The future is not a place you can refuse to go. It is a place you are always, inescapably moving toward. This is the deepest difference between space and time, as you normally experience them. Space offers choices. Time offers none. Inside the event horizon, this distinction flips. The direction that points toward the center of the black hole, the direction of decreasing distance, stops behaving like a direction in space and starts behaving like the flow of time. Falling toward the center is no longer something you could choose to avoid by turning around or firing an engine. It becomes as inevitable, as unstoppable, as the arrival of tomorrow. The center of the black hole is not a place sitting somewhere ahead of you in space. It has become a moment waiting for you in your future. And just as no force in the universe can stop you from reaching tomorrow, no force, no engine, no power imaginable can stop you from reaching the center. Consider how completely this dismantles our intuition about escape. Outside the black hole, you might imagine that with a powerful enough rocket, you could fight your way back out. The reason you cannot is not that the rocket is too weak. It is that there is no longer any direction that leads out. Every path through space inside the horizon, every direction you could possibly point yourself, leads inevitably toward the center. The same way every path through time leads toward the future. Firing your engines to escape the singularity would be exactly as pointless as firing your engines to escape next Tuesday. The destination is not in front of you. It is in your future, and the future cannot be outrun. This is why nothing escapes a black hole, and the real reason is far stranger than the simple story of gravity being too strong. It is not that gravity holds you down. It is that the geometry of space and time has been so twisted that the center of the black hole occupies your future, and the outside universe has been removed from the set of places you are able to reach. You are not trapped the way a prisoner is trapped behind walls. You are trapped the way all of us are trapped in the flow of time, unable to move in any direction but forward, toward the one moment that is coming for us all. And that moment is coming quickly. Once you cross the event horizon of Sagittarius A star, the time you have left before reaching the center is shockingly brief. Not years, not days. For a black hole of 4 million solar masses, the time from the horizon to the center, measured by your own watch, is less than a minute. Perhaps only half a minute. You would have crossed the most absolute boundary in the universe, and then you would have a handful of heartbeats, a single held breath, before the journey reached its end. For the truly colossal black holes, the giant in Messier 87, you might have closer to a full day inside, falling through a darkness larger than our solar system. But for the black hole at the heart of our own galaxy, the entire interior journey, from the silent crossing to the final moment, would last about as long as it takes to read a single page aloud. So what waits at the center? The equations of general relativity give a clear and disturbing answer, and that answer is the place where the theory destroys itself. As you fall toward the center, the tidal forces that were so gentle at the horizon begin, at last, to grow. They grow slowly at first, then faster, then with terrifying speed. The stretching between your feet and your head, which you could not even feel as you cross the boundary, becomes noticeable, then strong, then unbearable. In your final fraction of a second, the spaghettification that the giant black hole spared you at the edge arrives all at once. You are stretched, drawn out, torn apart, your body, your cells, your molecules, your atoms, pulled into a thread of particles plunging toward the center. And the center itself, according to the mathematics, is a place of infinite density and infinitely curved space. We call it the singularity. The equations say that all of the mass that fell into the black hole, all of those millions of suns worth of matter, is crushed down not into a small ball, not into a dense core, but into a single point of zero size and infinite density. A place where the curvature of space and time becomes infinite. A place where the equations of general relativity simply stop producing sensible answers, spitting out infinities where there should be numbers. In 1965, the British physicist Roger Penrose proved something profound about these singularities. Many physicists had hoped that the singularity was an illusion, an artifact of assuming a perfectly round, perfectly symmetric collapse, the kind of unrealistic perfection that nature never actually provides. Penrose showed that this hope was false. Using powerful new mathematical techniques, he proved that once a region of space collapses past the point of forming an event horizon, a singularity is essentially unavoidable. It is not a quirk of perfect symmetry. It is a deep and general feature of how gravity behaves when matter collapses completely. For this work, which reshaped our understanding of black holes, Roger Penrose was awarded the Nobel Prize in Physics in the year 2020, more than half a century after he did it. But here is the honest truth, the one that working physicists will tell you if you ask them directly. We do not actually know what is at the center of a black hole. The singularity is not really a prediction we trust. It is a warning sign. When a theory predicts that a quantity becomes infinite, it is almost never telling you that something infinite truly exists. It is telling you that the theory has been pushed beyond the limits of where it works, and that some deeper, more complete theory is needed to describe what really happens. General relativity, Einstein's magnificent theory of gravity, predicts its own breakdown at the center of every black hole. The infinities are the sound of the theory failing. The singularity is the place where our best description of reality openly admits that it does not know. To truly describe the center of a black hole, we would need a theory that combines Einstein's gravity with the strange rules of quantum mechanics, the physics of the very small. We would need a theory of quantum gravity. And despite a century of effort by some of the most brilliant minds who have ever lived, we do not have one. We have candidates, fragments, promising ideas with names like string theory and loop quantum gravity, but no complete and confirmed answer. So the deepest question of all, the question of what truly lies at the heart of these objects, remains genuinely open. The honest answer is that nobody knows. The center of a black hole is, right now, one of the few places in the entire universe where we can say with certainty that our knowledge runs out, where the map of physics goes blank, and where the only label we can write is the oldest and most honest one in all of science. Here we do not yet understand. There is something else we have been quietly ignoring, a simplification we made at the very start of our fall, and it is time to confront it. Everything we have described so far, the perfectly round event horizon, the single point of infinite density at the center, comes from the simplest possible kind of black hole, the kind that Carl Schwarzschild first described from the trenches. That kind of black hole does not spin and carries no rotation at all. It is the clean, ideal textbook case. But the real black holes scattered throughout our universe are almost never like that. The real ones spin. Think about where black holes come from. They form from collapsing stars, and stars rotate. They grow by swallowing gas from swirling disks, and that gas carries rotation with it. When something that is spinning collapses inward, its spin does not vanish. It speeds up, exactly the way a spinning skater whirls faster as she pulls in her arms. By the time a star has collapsed into a black hole, that inherited rotation has become ferocious. Many black holes spin so fast that their outer edges are whirling around at a sizable fraction of the speed of light itself. We are not falling toward a still, silent sphere. We are falling toward a colossal, spinning vortex in the very fabric of reality. The mathematics of a spinning black hole was not worked out until 1963, nearly half a century after Schwarzschild, when a New Zealand mathematician named Roy Kerr found the solution to Einstein's equations for a rotating mass. It was a fearsomely difficult piece of work, and what it revealed was a structure far richer and far stranger than the simple Schwarzschild picture. A spinning black hole does not merely sit there bending space, it drags space around with it. This effect has a name. It is called frame dragging, and it is one of the most disorienting predictions in all of physics. Near a spinning black hole, space itself is not still. It is caught up in the rotation, swept around the hole like water spiraling down a drain, dragged along in the direction of the spin. Come close enough to a rapidly spinning black hole, and you would find that simply standing still becomes literally impossible. Not difficult, impossible. There is no engine powerful enough, no force strong enough to hold you motionless against the turning sky, because space itself is flowing around the hole, carrying everything within it along for the ride. You would be swept around the black hole whether you wished it or not, simply because the space you occupied was itself in motion. Around a spinning black hole there is a region, just outside the true point of no return, where this dragging becomes inescapable. We call it the ergosphere, from an old word meaning work, and it has a remarkable property. Within the ergosphere you are forced to move along with the hole's rotation, and yet, crucially, you can still escape. You have not yet crossed the final horizon, and this opens a strange possibility. In 1969, Roger Penrose, the same mind who proved the inevitability of singularities, realized that you could actually steal energy from a spinning black hole. If you sent an object into the ergosphere and split it in two, letting one piece fall through the horizon while the other flew back out, the escaping piece could emerge carrying more energy than the hole had going in. The extra energy would be drained from the rotation of the black hole itself, the great vortex spinning very slightly slower as a result. A spinning black hole, it turns out, is not only a trap, it is a vast reservoir of rotational energy, and nature knows how to tap it. The colossal jets of matter that some black holes fire across thousands of light years, among the most violent beacons in the entire cosmos, are thought to be powered in part by exactly this, by energy harvested from the spin of a giant black hole. But the most extraordinary difference lies at the very center. In the simple Schwarzschild black hole, all the matter is crushed to a single point, the singularity, a place of infinite density. In a spinning black hole, the mathematics says something different, something almost more unsettling. The singularity is not a point at all. It is a ring. The crushed matter, whirling at tremendous speed, is flung outward by its own rotation into an infinitely thin loop. A ring of infinite density spinning at the heart of the darkness. And a ring, unlike a point, is something you might imagine passing through. This is where the mathematics begins to whisper truly strange things, and where we must be especially honest about how little we know. On paper, in the idealized equations of a perfectly spinning black hole, the structure inside is more elaborate than the simple picture we drew before. There is not one horizon, but two, an outer one and an inner one. And beyond that inner horizon, the equations suggest, the relentless future-pointing fall toward the center finally relaxes. The singularity becomes something you could, in principle, avoid, steering around the ring rather than being driven helplessly into it. Some solutions even hint, on paper, at strange paths that might lead onward, away, to somewhere else entirely. But here we must stop and tell the truth, because this is exactly the kind of place where beautiful mathematics can lead us badly astray. These elegant inner structures are almost certainly not what a real traveler would find. The calculations that produce them assume a perfect, eternal, undisturbed black hole sitting alone in an empty universe. The real universe is nothing like that. Real black holes are bombarded with infalling matter and radiation, and that endless rain, blue-shifted to unimaginable energies as it falls, is expected to pile up at that inner horizon and build into a wall of catastrophic intensity. Most physicists who study this believe that the gentle inner regions of the ideal equations would, in any real black hole, be crushed and sealed off by this build-up, the inner horizon transformed into a second and lethal frontier. The doorways that the pure mathematics seems to offer are, in all likelihood, slammed shut by the messy reality of a universe full of falling matter. So the spinning black hole, the true and common kind, deepens every mystery rather than resolving it. It drags space into a whirlpool. It hoards energy in its rotation. It replaces the central point with a spinning ring of fire, and it teases us, in the cold elegance of its equations, with structures and passages that the real universe almost certainly forbids. We chose, tonight, to imagine the simplest fall into a still and quiet hole. But the black holes that truly haunt the dark are spinning monsters, whirling the very fabric of space around themselves. And even now, after everything we have learned, their deepest interiors remain a country that no theory we trust has ever truly mapped. And yet, the black hole has one more secret to reveal, perhaps the strangest of all. For most of the 20th century, physicists believed that black holes were truly, perfectly black, that they only swallowed, never gave anything back, that they were eternal, growing forever, taking in matter and light and information, and never releasing a single particle. And then a young physicist in a wheelchair did a calculation that no one expected, and discovered that black holes are not eternal after all. They glow, they leak, and given enough time, every black hole in the universe will slowly, faintly, inevitably evaporate into nothing. The young physicist was Stephen Hawking, and in 1974 he published a result that stunned the scientific world, and that he himself had initially found hard to believe. He had been thinking about what happens to the empty space right at the edge of a black hole, and he had brought together two great theories that rarely speak to each other. On one side, Einstein's theory of gravity, which governs the very large. On the other, quantum mechanics, which governs the very small. When he put them together at the event horizon, something extraordinary fell out of the mathematics. Black holes, he found, are not perfectly black. They glow ever so faintly, with a temperature and a light all their own. There is a human story here that is worth pausing over, because it is one of the most remarkable in all the history of science. Stephen Hawking made this discovery, the discovery that the darkest objects in the universe quietly glow, while living under a sentence that would have stopped almost anyone else. As a young man at Cambridge in his early 20s, full of promise and not yet famous, He had begun to notice that his body was failing him. He grew clumsy. He stumbled. He fell. And then came the diagnosis. He had a rare and merciless disease of the nervous system, one that slowly severs the brain's command over the muscles, leaving the mind perfectly sharp and clear while the body, piece by piece, stops obeying. He was told he had perhaps 2 years left to live. He was 21 years old. But the 2 years passed, and Hawking did not die. The disease advanced slowly, far more slowly than anyone had predicted, stealing his movement inch by inch across the decades. He lost the use of his legs, and then his hands, and eventually almost every voluntary muscle in his body. In time, he could move little more than a few fingers, and then, not even that. He lost the power of speech, and came to talk through a computer, choosing his words one at a time, his sentences emerging in a flat, patient electronic voice that the whole world would eventually come to know. And through all of it, his mind never stopped working. It was during these years, already bound to a wheelchair, already unable to write out an equation in his own hand, that Hawking did the very work we are speaking of now. He carried the mathematics in his head, turning it over and over in the one place the disease could never reach. He pictured the empty space at the edge of a black hole, and he saw where everyone else had seen only perfect blackness, a faint and inevitable glow. A man who could barely move his own body had reached out with his mind alone and discovered that the most powerful objects in the universe are slowly, quietly dying. He lived not 2 years but more than 50, passing away at the age of 76, having become the most famous scientist of his age. And the discovery that bears his name, the faint radiation seeping outward from the edge of every black hole in the cosmos, remains his greatest gift to physics, and one of the deepest clues we have to the mysteries still hidden inside these objects. To understand how a black hole could possibly glow at all, Hawking had to look at empty space itself in a completely new way. To understand why, you have to abandon another comfortable idea. You probably think of empty space as truly empty, as nothing at all. But according to quantum mechanics, empty space is not empty. It seethes. At the smallest scales, in the briefest instants, pairs of particles are constantly flickering into existence and then vanishing again, born from the energy of the vacuum itself and annihilating almost instantly. This restless boiling of empty space has been measured in laboratories. It is one of the strangest and best confirmed facts in physics. Empty space is not a quiet void. It is a churning sea of fleeting particles, appearing and disappearing too quickly to ever be caught. Now imagine this boiling vacuum right at the edge of a black hole. A pair of particles flickers into existence on the very lip of the event horizon. Normally they would find each other again in an instant and vanish, leaving nothing behind. But here, at the edge of the black hole, something can go wrong. One member of the pair can fall across the horizon, lost forever, while the other escapes outward into space. They can never reunite. The escaping particle flies away from the black hole, carrying energy with it. And to balance the books, to keep the total energy in agreement, the black hole must give up a tiny piece of its own mass. The escaping particles, streaming away from the horizon, are what we now call Hawking radiation. And every particle that escapes means the black hole has grown infinitesimally smaller. This is a simplified picture of a far deeper calculation, but it captures the heart of it. Black holes leak. Slowly, faintly, particle by particle, they radiate their mass away into the surrounding darkness. Over time, a black hole left entirely alone, with nothing falling into it, will shrink. It will lose mass. And eventually, after an almost unimaginable span of time, it will evaporate completely, vanishing in a final faint flicker, leaving behind only the radiation it shed and an empty patch of space where a monster once was. The temperature of this radiation depends on the size of the black hole, and the relationship is the opposite of what you might guess. Small black holes are hot. Large black holes are cold. A black hole the mass of our Sun would have a temperature so low that it is almost beyond comprehension, far colder than the empty space around it. In fact, here is a strange consequence. The universe today is filled with a faint afterglow of warmth left over from its birth, a background radiation that sits at about 2.7 degrees above absolute zero. A black hole the mass of our Sun is actually colder than that background. This means that right now, today, the great black holes of our universe are not evaporating at all. They are absorbing more warmth from the surrounding cosmos than they radiate away. They are still growing. Only in the unimaginably distant future, when the universe is expanded and cooled and faded almost to nothing, colder even than the black holes themselves, will these giants finally begin to truly evaporate. And when they do, the timescales involved are so vast that they make the current age of the universe look like the blink of an eye. A black hole the mass of our Sun, left to evaporate in a cold and empty future, would take a length of time written as a 1 followed by 67 zeros years to disappear. The supermassive black holes, the giants at the centers of galaxies, would take far longer still, a span of time written as a 1 followed by 100 zeros years, a number so enormous it has its own name, the Google, and a duration so long that the word eternity hardly seems an exaggeration. The universe is not yet a fraction of a fraction of a fraction of the way through the lifetime of its black holes. They are, for all practical purposes, the last things that will remain. Long after the last star has burned out, long after the galaxies have gone dark and cold, the black holes will still be there, glowing ever so faintly, slowly bleeding away into the eternal night. Hawking's discovery did something else, something that turned out to be even more profound than the radiation itself. It revealed that black holes obey the laws of heat and energy, the laws of thermodynamics, just like a hot cup of coffee or a burning fire. A few years earlier, a young physicist named Jacob Bekenstein had made a daring suggestion. He proposed that black holes must possess a quantity called entropy, a measure of disorder, of hidden information, of all the ways the inside could be arranged. This sounded almost heretical at the time. But Bekenstein argued that without it, black holes would violate one of the most sacred laws in all of physics, the law that says disorder in the universe can never decrease. If a black hole had no entropy, you could throw a messy, disordered object into it and erase that disorder from the universe, breaking the law. So the black hole itself must carry the entropy instead. When Hawking's calculation confirmed that black holes have a temperature, it confirmed Bekenstein's idea as well. Black holes do have entropy, and the form of that entropy is one of the deepest mysteries in physics. For an ordinary object, the amount of hidden information it can hold grows with its volume, with how much space is inside it. A bigger box holds more. But the entropy of a black hole does not grow with its volume. It grows with the area of its event horizon, with the size of its surface. All of the staggering hidden information of everything that ever fell into the black hole is somehow encoded not in the volume within, but on the two-dimensional surface that surrounds it, like a message written on a vast spherical page. This astonishing fact, that the information content of a region of space might be written on its boundary rather than filling its interior, gave birth to one of the boldest ideas in modern physics, the holographic principle, the suggestion that our entire three-dimensional reality might, in some deep sense, be encoded on a distant surface, like a hologram. But that is a journey for another night. For now, hold on to this. Black holes are not the eternal, perfect, bottomless pits we once imagined. They are hot, in their own faint way. They glow. They leak. They obey the laws of heat and energy. They carry entropy on their surfaces, and they die, slowly, over spans of time so vast that they defy all imagining, dissolving at last into the cold and the dark. The most permanent objects in the universe are, in the end, still mortal. Even the black holes will not last forever. But the discovery that black holes evaporate created a problem, a paradox so deep and so troubling that it has occupied the finest minds in physics for half a century and remains unresolved to this day. It strikes at the very foundation of what we believe about reality, about information, and about whether the past can ever truly be erased. To see it clearly, we have to ask a simple question with no comfortable answer. When something falls into a black hole, and the black hole later evaporates away to nothing, where does the information about that something go? This question sounds abstract, but it cuts to the very heart of what physics is. One of the most fundamental principles in all of science is that information is never truly destroyed. Burn a book, and it seems lost, but in principle every detail is still encoded in the smoke, the ash, the heat, and the light it gave off. If you could track every particle perfectly, you could, in theory, reconstruct the original book from its ashes. The information is scrambled beyond any practical recovery, but it is never erased. Quantum mechanics insists on this. The past leaves a permanent imprint. Nothing is ever simply gone. Now apply this to the black hole. Something falls in, carrying information, all the unique details of its structure and history. The black hole gives no sign of what it swallowed. And then, over those vast spans of time, the black hole slowly evaporates through Hawking radiation, shrinking until nothing remains. Here is the problem. According to Hawking's original calculation, the radiation that escapes is purely random, purely thermal, like the featureless glow of a warm object. It carries no information at all about what fell in. So when the black hole finishes evaporating, when it vanishes entirely, the information about everything that ever fell into it appears to be gone. Not scrambled, not hidden, erased from the universe completely. This is the black hole information paradox, and it is far more serious than it might first appear. If information can truly be destroyed inside a black hole, then one of the deepest principles of quantum mechanics is broken. The past would not always leave an imprint. The universe would have a way to forget. Reality would contain a kind of cosmic shredder, capable of removing history from existence without a trace. For most physicists, this is unacceptable. It would mean that the foundations of physics are simply wrong. And yet Hawking's calculations seem to point directly at it. Stephen Hawking himself, in 1976, argued that information truly is lost, that the black hole really does destroy it. Most of his colleagues found this almost impossible to accept, but no one could find the flaw in his reasoning. The debate grew so intense that it produced another famous wager. In 1997, Hawking and his colleague Kip Thorne bet a physicist named John Preskill that information falling into a black hole is destroyed forever. Preskill bet that it must somehow survive, because the laws of quantum mechanics demanded it. The disagreement was not a small technical quarrel. It was a battle over which of our deepest theories would have to give way. Over the following decades, the tide slowly turned against Hawking's original position. Two physicists in particular, Leonard Susskind and Gerard Hooft, championed the idea that information must be preserved, and they developed a strange and beautiful proposal to explain how. They suggested that the information is not destroyed and not simply lost inside. Instead, in some sense, it is both inside the black hole and smeared across its surface at the same time, encoded in the horizon and carried out, eventually, in the subtle patterns of the escaping radiation. No single observer, they argued, could ever see both copies at once and catch the universe in a contradiction. An observer falling in sees the information go inside. An observer staying outside sees it imprinted on the horizon and slowly released. Because no one can ever compare the two views, there is no paradox. This idea became known as black hole complementarity, and for a time it seemed to offer a way out. In 2004, after years of resistance, Stephen Hawking publicly conceded the bet. He announced that he now believed information is not destroyed after all, that it does escape from black holes, however subtly. He paid John Preskill his winnings. The cosmic shredder, it seemed, did not exist. The past was safe. But the story did not end there, and physics rarely allows itself a clean resolution. In 2012, a group of 4 physicists, working through the mathematics of complementarity with great care, found that it seemed to break down under close examination. To keep information from being destroyed, they argued, the gentle, featureless event horizon we have been describing might not be gentle at all. Instead, the horizon might be a violent wall of intense energy, a barrier of high-energy particles that would incinerate anything that touched it. They called this a firewall. And it presented a brutal choice. Either you give up the principle that information is preserved, or you give up Einstein's principle that an observer falling freely through the horizon of a large black hole feels nothing at all. One of these cherished ideas, it seemed, had to be wrong. This reignited the entire debate, and it remains alive today. The firewall proposal suggested that perhaps the peaceful crossing we imagined, the silent slide through the horizon with no sensation at all, might be an illusion, and that instead you would meet a wall of fire at the edge. Most physicists find the firewall deeply troubling, because it violates one of the most beautiful and well-tested ideas in all of physics, the principle that gravity feels the same as ordinary acceleration, and that nothing dramatic should happen at the horizon of a giant black hole. The argument is still unsettled. Brilliant people line up on different sides of it. In recent years, new and powerful mathematical work has offered fresh hope that information does escape after all, and that quantum mechanics survives intact, without requiring a wall of fire. Around 2019 and 2020, physicists found new ways of calculating how information leaks out of an evaporating black hole, and the results suggested that the radiation does, in the end, carry the information out, just as quantum mechanics demands. These calculations are subtle, and they are still being understood and debated, but they represent real progress on a problem that has resisted solution for nearly 50 years. The honest summary is this: we now strongly believe that information is preserved. We are still working out exactly how, and the black hole remains the single greatest testing ground for the deepest questions in all of physics. Part of what made this recent progress possible was a breathtaking idea about the deep connection between two things that seem, at first, to have nothing to do with each other. In 2013, the physicists Juan Maldacena and Leonard Susskind proposed that two particles linked by the strange quantum thread we call entanglement, two particles whose fates remain bound together no matter how far apart they drift, might be connected by something far more concrete than anyone had imagined. They suggested that entanglement and the bridges of warped space we call wormholes might be at the very deepest level the same thing, that the invisible quantum link between two distant particles is, in some sense, a tiny tunnel through the geometry of space itself. If that is true, and a growing number of physicists now suspect that something like it is, then it changes how we think about the inside of a black hole entirely. The radiation leaking away from an evaporating black hole is deeply entangled with the matter that fell in. And if entanglement is woven from the same fabric as the shape of space, then the information trapped inside may not be sealed off as completely as it seems. There may be a sense in which parts of the interior are secretly connected to, even secretly part of, the radiation drifting away outside. In the recent calculations, physicists found that as a black hole slowly evaporates, a hidden region deep inside, which they gave the gentle name of an island, gradually comes to be counted as part of the outside radiation, allowing the trapped information to find its way back out into the universe after all. These ideas are abstract, and they live at the very frontier of human understanding, written in mathematics that only a few hundred people on Earth can fully follow. But the picture they paint is quietly astonishing. The inside of a black hole and the radiation escaping from it may not be two separate things at all, but two views of a single, deeply entangled whole, stitched together by threads of warped space too subtle for us to have noticed until now. The deeper we look into the darkness, the more it begins to seem that a black hole is not a place where reality ends, but a place where the hidden connections that hold reality together are finally laid bare. Because here is what makes the black hole so precious to science, and so endlessly fascinating. It is the one place in the universe where our two greatest theories, general relativity and quantum mechanics, are forced into the same room and openly contradict each other. Relativity describes gravity and the shape of space and time with perfect accuracy across the cosmos. Quantum mechanics describes the world of particles and information with perfect accuracy at the smallest scales. Both theories are triumphs. Both have passed every test we have ever devised. And at the event horizon of a black hole, they disagree. Resolving that disagreement, finding the deeper theory that contains both, would be one of the greatest achievements in the history of human thought. The black hole is not just a monster in the dark. It is a doorway. It is the place where the next revolution in physics is waiting to be found. And the most wonderful thing of all is that we are no longer limited to imagining these objects from afar. For most of history, the black hole was a thing of equations and inference, a shadow known only by its effects. That changed forever on the 14th of September, 2015. On that day, an instrument called the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a faint tremor in the fabric of space itself. A ripple in space and time that had been traveling toward us for more than 1 billion years. It was the signal of two black holes, one about 36 times the mass of our Sun, and the other about 29, spiraling together in the dark and merging into one. In the final fraction of a second of that collision, more than 1 billion light years away, an amount of mass equal to about 3 times our entire Sun was converted into pure gravitational energy, sent rippling outward across the universe at the speed of light. We did not see it with our eyes, we felt it, in the gentle stretching and squeezing of space, measured by instruments so sensitive they can detect a change smaller than the width of an atomic nucleus. For the first time, we had heard two black holes collide. The monsters were no longer only theory. We could listen to them. It is worth lingering on what that detection truly was, because it remains one of the most astonishing achievements in the entire history of science. For 100 years, Einstein's theory had predicted that violent events in space should send ripples through the fabric of space and time itself, waves of stretching and squeezing that travel outward at the speed of light. But the waves were thought to be so faint that Einstein himself doubted they could ever be measured. To catch one, you would need to detect a change in length smaller than a fraction of the width of a single proton, across instruments miles long. For decades, it seemed flatly impossible. And yet, on that September morning in 2015, two enormous detectors, one in the state of Louisiana and one in the state of Washington, thousands of miles apart, both twitched at almost the very same instant, registering the same faint, rising tremor. When the scientists translated that tremor into a sound that human ears could hear, it was a single rising note, sweeping upward in pitch and growing louder over about 1/5 of a second, before stopping abruptly. Physicists call it the chirp. It is the sound of two black holes in their final dance, spiraling closer and closer, whirling around each other faster and faster as they spent the last of their orbital energy, until they touched, and merged, and fell silent. A journey of more than 1 billion years, ending in 1/5 of a second of sound. Consider the violence of that final moment. Two black holes, each many times the mass of our Sun, circling each other hundreds of times every second in the instant before they joined, sweeping around at a large fraction of the speed of light. When they merged, in that final convulsion, the power they poured out in gravitational waves briefly exceeded the combined light of every star in the entire observable universe. Not the power of a single galaxy, not the power of 1 billion galaxies. The combined output of every star that exists, all of it, surpassed for a fraction of a heartbeat by two black holes colliding in the dark, more than 1 billion light years away. And none of that titanic energy came out as light. It came out as a shudder in the shape of space itself, a wave that washed silently across the universe for over 1 billion years, and finally, gently, stretched the Earth by less than the width of an atom on a quiet morning, and was caught. The scientists who built the instruments that heard it, among them Rainer Weiss, Barry Barish and Kip Thorne, were awarded the highest prize in physics 2 years later, in 2017. But the deeper meaning of that morning was this. We had opened an entirely new sense. For all of human history, we had studied the universe with light, with our eyes and our telescopes, gathering the radiation that things give off. Now for the first time we could feel the universe trembling. We could detect events that give off no light at all, like two black holes meeting in perfect darkness, by the ripples they send out through space. Since that first detection, we have felt many more, the universe revealing itself to be filled with these silent collisions, black holes and neutron stars merging again and again across the deep dark, each one sending out its faint and final chord for us to catch. The monsters had been invisible for the whole of history, and then, at last, we learned to hear them sing, and we have even learned to see them with cinematic precision before our telescopes could. In 2014, the physicist Kip Thorne worked with a team of visual artists to create an image of a spinning black hole for a film, using the real equations of general relativity to calculate exactly how the light would bend around it. The result was so accurate and so detailed that it revealed patterns in the warping of light that the scientists had not fully anticipated, and it became the subject of a genuine scientific paper. A monster from the deepest mathematics of physics had been rendered, faithfully, in light, and in doing so, it taught the very scientists who made it something new about how these objects truly look. We have traced the full journey now. We have followed the fall from the first gentle drop across the silent and invisible horizon, through the place where space and time trade roles, down to the singularity where our knowledge runs out, and outward again to the faint glow of evaporation and the deepest paradox in all of physics. There is only one question left. Not what a black hole is, not what it does, but what it means for you, lying here in the dark, made of atoms that were forged in dying stars, contemplating the places in the universe where everything you are could vanish without a sound. There is something almost unbearable about the black hole when you sit with it quietly, the way you are sitting now. It is the place in the universe where everything ends, not slowly, not gracefully, but absolutely. Whatever falls in is removed from the rest of reality forever, its light extinguished, its information scrambled beyond any recovery, its very shape erased as it is drawn down toward a center where the laws of physics themselves dissolve. The black hole is the universe's final full stop. It is the closest thing that nature offers to true oblivion, and there are millions upon millions of them, scattered through every galaxy, with one of the largest sitting at the very center of our own, anchoring the slow turning of every star we have ever named. It would be easy, lying here in the dark, to find this terrifying, to feel the cold indifference of a cosmos that builds engines of pure erasure and scatters them through the night. The universe did not make black holes for us. It did not make them against us either. They are simply a consequence of gravity, following its own rules to their final conclusion, and gravity does not know that we exist. The universe is vast beyond comprehension, and almost all of it is empty, and cold, and utterly unconcerned with whether you live or die or ever existed at all. Against the scale of the black holes, against the spans of time over which they slowly evaporate, a human life is so brief that it barely registers. We are here for a flicker, and then we are gone, and the dark goes on. And yet, hold on to that small word, because everything turns on it. And yet, perhaps the lesson of the black hole is that we are nothing, that our brief lives are insignificant against a cosmos that swallows even light, that the only honest response to such a universe is despair. Or perhaps the lesson is exactly the opposite. Perhaps the truly extraordinary thing is not the black hole at all, but the fact that there is something in this universe capable of understanding it. Consider what you have done tonight, lying still in the dark. You, a small, warm, fragile creature, made of atoms that were forged in the hearts of dying stars and scattered across space billions of years before the Earth existed, have reached out with your mind and grasped the nature of the most extreme objects that physics allows. You have understood how time bends near them. You have followed the fall across the horizon. You have stood, in your imagination, at the edge of the place where knowledge ends. The black hole cannot do this. It cannot wonder about you. It cannot ask a single question. For all its monstrous power, it is utterly without understanding. And you, who could be erased by it without a trace, understand it. These are not questions with final answers, and they are not meant to be. Different people, lying in different rooms in the dark, will draw different conclusions from the same cold facts. Some will feel diminished by the scale of it all, and there is truth in that. Some will feel strangely uplifted, awed by the sheer improbability of being a conscious witness to such a universe, and there is truth in that as well. You do not have to choose tonight. You do not have to resolve it. You are allowed to hold both feelings at once, the smallness and the wonder, the dread and the awe, the way the universe itself holds both the cold and the warmth, the darkness and the light. The tension does not need to be solved. It only needs to be felt. So let us step back, one final time, and take in the full scale of the thing. You exist in a universe that stretches at least 93 billion light years across, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, and woven through all of it, at the heart of nearly every galaxy, the silent and patient black holes, growing now, evaporating in a future so distant it has no meaning. The light from the most distant galaxies we can see has been travelling toward us for more than 13 billion years. Set out before the Earth existed, before the Sun existed, carrying images of a younger cosmos that may, by now, have changed beyond recognition. You are a single point of awareness inside all of this. A brief gathering of stardust that learned, somehow, to look up and ask why. You are smaller than you can possibly imagine, and you are rarer than you can possibly imagine. Both of these are true. Neither one cancels the other. The black hole shows us the limit of things. It shows us where matter ends, where light ends, where time and space themselves come apart, where even our finest theories fall silent and admit their ignorance. It is a monument to everything we do not yet understand. But a limit is not only an ending. A limit is also an invitation. Every time human beings have found the edge of what they know, the edge of the map where someone has written that knowledge runs out, we have eventually found a way to push it further. The singularity at the center of the black hole, the paradox at its horizon, the deeper theory that would unite gravity and the quantum world, all of these are not walls. They are doorways, waiting. And somewhere out there, perhaps already alive, perhaps not yet born, is the mind that will walk through them and understand what we could only wonder about, lying in the dark. There is room in this cold and indifferent universe for meaning, but it is not handed to us by the stars. We have to make it ourselves, here in the warmth of our brief and improbable lives, in the questions we choose to ask and the wonder we choose to feel. The black hole will not give us meaning. It does not have any to give. But it can give us perspective. It can remind us how astonishing it is to be here at all, to be warm and awake and curious in a cosmos that is mostly none of those things. The dark is not our enemy. The dark is simply most of what there is, and we are the small, bright exception, gathered for a little while against it. So rest now. There is nothing to fear in any of this. The black holes are unimaginably far away, and they will not come for you tonight, or in any night you will ever know. They will go on turning slowly at the centers of their galaxies, swallowing the occasional star, glowing ever so faintly into the eternal dark, long after everything you have ever loved has faded into the same gentle silence. That is not a tragedy. It is simply the shape of things. The universe is vast and old and patient, and it keeps almost everything in the end. But not the warmth in this room, not the breath moving slowly in your chest, not the quiet wonder you carried with you into the dark tonight. The dark is deep, and it is patient, and one day it will hold us all, but not here, not tonight, not yet.